AB Calculus Note Card 65, Optimization Problems. This is the 65th video lesson in the series inspired by Stacy McMullen, formerly of the Dallas Independent School District, who developed this note card system. This lesson is very much analogous to note card lesson 31, the Extreme Value Theorem. Optimization means to maximize or minimize a quantity or situation. To optimize, find the absolute maximum or absolute minimum and apply that amount to the particular situation. And we're going to examine one AP Calculus free response problem that fleshes this out. A particle moves along the x-axis so its velocity at time for t between 0 and 6 seconds is given by a differentiable function v. And I said seconds, right? And it doesn't say seconds anywhere. We're just going to assume seconds. It doesn't say that specifically. The velocity is 0 at t equals 0, t equals 3, and t equals 5. And the graph has horizontal tangents at t equals 1 and t equals 4. The areas of the region bounded by the t-axis and the graph of v on the intervals from 0 to 3, 3 to 5, and 5 to 6 are 8, 3, and 2 respectively. And so what that means is this area bounded below is going to be 8, and this area between 3 and 5 bounded above is an area of 3, and this last area is going to be 2 below the x-axis. At time t equals 0, the particle is at x equals -2. And I'm just going to say seconds, and I'm just going to make that assumption. I can do that. Okay, you might recall, I hope you recall, this little chart here that we've looked at several times. F prime, F double prime, and we had this plus minus, increasing, decreasing, concave up, concave down, and below on the F prime level we had plus below the F increasing, minus below the F decreasing, and we had increasing here, decreasing here, and finally on the F double prime row we had plus or minus. Now what we're going to do in this case integration, we're going to have a row above here which is going to be called sometimes capital F of t, or the integral of f of I said t, we're using t here, and what they call that in this situation here is x. So we're going to call this x of t because that's what they use in the problem. In this row down here, f is going to be analogous to v of t. And what we have above the plus sign in the v of t function is x of t increasing, and above the negative sign in the v of t function we have x of t decreasing. So our analysis is going to make use of these relations right here. In the v of t, essentially what we have is we have critical numbers, and the critical numbers are given to us by the velocity being 0. Now you remember critical numbers are where a function is equal to 0 or undefined. Well, here we're going to have our critical numbers are going to be 0, 3, 4, not 4, 5, 0, 3, 5, and our endpoint is 6. And I'm going to put v of t up above and x of t below. So we have between 0 and 3 is v of t above the t-axis or below. It is below. Between t equals 3 and t equals 5 is v of t above the axis, x-axis, or t-axis, or below, above. Between 5 and 6 is v of t above the t-axis, x-axis, or below. I'm getting t and x mixed up. And so we know, therefore, that x of t is decreasing between t equals 0 and t equals 3. We know that x of t is increasing between t equals 3 and t equals 5, and lastly decreasing between t equals 5 and t equals 6. What we're going to do for analysis purposes is do what we did earlier on note card 31. We're going to run what we call a candidate test. Because what are we trying to find here? For t between 0 and 6, I say seconds here, find both the time and position of the particle when the particle is farthest to the left. Justify your answer. And so what we're going to have here is t and x of t. And we see at time t equals 0, the particle is at -2 seconds. As far as our other endpoint, that's going to be a candidate, so I'm going to put 6 way down here below. And then our critical numbers between 0 and 6 are where t equals 0 at t equals 3 and t equals 5. So I'm going to place 3 and 5 here as well. Well, starting at 0, and where t equals 0, x of t is -2, given to us as would be like an initial condition is what we call it, is v of t negative or positive between t equals 0 and t equals 3? Well, negative. So x of t is decreasing. And we are told what it is decreasing by is we are subtracting 8. So -2 minus 8 is -10. Next, between t equals 3 and t equals 5 is x of t increasing? Yes, it is, because you have the positive sign for v of t, and x of t is increasing. And what is going to be increased by? By 3 units. So -10 plus 3 is -7. And then in the final interval between t equals 5 and t equals 6 is v of t is v above or below the x-axis? Below the x-axis. And we are going to subtract, therefore, 2 units. So -7 minus 2 will be -9. So there we have it. Find both the time and position of the particle. So at t equals 3, what does it say to the left? The position is x of t equals x of 3 equals -10. So the particle is farthest to the left left at t equals 3. And justify. Okay, well, we have done our justification. And our justification is articulated in the candidate test. According to the Extreme Value Theorem, there must be a value be a minimum, and that value is -10. And we're not given the units in feet or seconds or anything, so this might be the best we can do. I hope you can see how this problem is quite analogous to what we examined earlier in Notecard 31 for the Extreme Value Theorem. I hope this has been helpful to you. Good luck, and thanks for viewing.